Hello and welcome back to Gaming Like It's 1979. Today we're going to continue our look at Turing Complete, a programming game, or a puzzle game, depending on how you want to look at it, which is in early access on Steam. Now, apparently a couple of patches have come out since we last looked at this game, so let's see what's changed. We have our map, which shows what we've unlocked over here, and also which levels we've completed. So this is new. In the last time we looked at this, rather than having a delay buffer, you actually built a little circuit that was self-referential, and a lot of players were having trouble with that. So now they've added something. They've added this delay buffer. Is it considered a gate? Let's see. No, memory. There we go. So we want to do something, I think they said 2 ticks, was that right? Same as input, but delayed by 2 ticks. So that sounds to me like we're going to do that. Have to remember how to actually connect things. All right, let's see if that worked. And it did, great. Okay, and then coming up here, we are locked on the input selector until we progress up this side here. So let's take a look at that one. Oh no, that one's locked too. So we have to go up both branches here. Counting signals. The output of this level is a binary counter where the first 3 pins correspond to 1, 2, and 4. Use the binary counter to count the number of signals. The solution for this level is not very neat and requires more components. Uh-oh. Well, let's take a look. And there's a hint. We could look at the hint if we want. You know what? Let's just go ahead and look at it off the bat. Same as what you did in the level. Odd number of signals. Circuitry for the 2's bits is what you did in Double Trouble, except when all 4s are on. So there's basically 3 paths here. There's the circuitry for the 1's bit, the circuitry for the 2's bit, and everything on this column here. All right, well, let's see. I don't remember. It looks to me like we might have copy and paste. Do we? Let's find out. So odd number of singles. Odd number of signals, huh? Can I copy this? I don't see a facility for copying, so we're just going to have to remember what this is, I think. Okay, so it's 3 XORs for odd number of signals. Let me hit paste and see if anything comes in. Nope. All right. So 3 XORs is what we said, right? And I believe they were arranged like so. And they did warn us that this isn't going to be messy. And that's part of why I am unapologetically looking at my own solution, is because I really don't want to have to, you know, zoom in and do some careful wiring. So they said this was 1s, 2s, and 4s. So which one of these is 1, which one is 2, and which one is 4? I'm going to assume that the top is the least significant bit. Can I step through here? That is correct, because this bit should be on. Okay, good. So then they said it was Double Trouble, except when all 4 are on. Well, let's go and grab our solution from Double Trouble. Oh no, and it's not here. They changed it. This level has 4 inputs. Output green when 2 or more of them are green. Tip, don't overthink this level. Well, if I'm not going to overthink it, if I'm going to be as silly as I possibly could be, as simple as I could be, then what I would say is we could put an AND gate for each matching pair of wires, and then output true when any one of those pairs, when any one of those ANDs is on. So we've got the first two will go there. The second two will go there. There is some perverse joy in making this wiring as awful as possible. All right, so 6 AND gates and 3 OR gates. All right, so that's over there. Can I? Oh, good. I have more space than I thought I had. That's wonderful. All right. To make this sane, I'm going to pull this over here. 1, 2. I guess I'm confused about why they're saying... because in the case where all 4 of these are on, we actually want this wire to be low. So we actually do need another AND gate. Let's work backwards here. Okay. So one necessary condition for this is that this OR is on. The other necessary condition is that all 4 of these are off. Right? Yeah. And so, no, that all 4 of these are not on, rather. If all 4 of these are on, then this has to be off. So, all 4 of those would be on with a standard matrix of ANDs, I think. Just 2 ANDs. There's probably a way to reuse all of these, but I'm not going to. I'm just going to keep it simple. Uh-oh. Are we out of space? Will this actually work? Looks like it's routing it logically, and we don't have to worry about physical space. That's good to know. And I could use a NAND, can't I? Yeah, I'll just use a NAND for this, I think. That's on. And if all 4 of these are on... No, I don't want to use a NAND because I'm going to end up needing another NAND. I'm going to need to invert this, basically, no matter what. All right, get rid of that. We're just going to use an AND. Okay. And then we're going to add an inverter here. And now we have 2 circuits we need. If the inverter goes here, and this goes there. And now we get that behavior that we want, that counter behavior. That sure looks like it's counting. All right, let's see if we did it. Okay, we got something wrong here. I think I actually just broke that. Oh my God, I really messed up. Let's try this again. Going from the top. This is meant to be. You know what? We're going to get rid of all of this. We're going to redo it. And this time, we're not going to use my weird pulled from wherever. I'm just going to wire it from here and hope that it works. 1 and 2. 1 and 3. 1 and 4. 2 and 3. 2 and 4. And then 3 and 4. Serves me right for trying to be clever. Great. Okay, fantastic. It unlocks a new manual entry on binary. Tip, there's no shame in using pen and paper. Thank you, passive-aggressive game. All right, now we're on to here. The input and outputs of this level are bytes instead of bits. One of the 2 new components you are given takes a byte and splits it into bits and the other does the opposite. Using those components, figure out how to double the input number. Okay. Byte maker turns 8 bits into a byte. Byte splitter expands a byte into 2 bits. So the implication here is that this input is a byte. Okay, so clearly we need to split it. And to double a number in binary, all we have to do is shift the bits down 1. Now, they don't say what to do with an overflow. My brilliant solution is going to be to completely ignore that question and just throw away any overflow. Right? So we're just going to do this, and that's it. Can I move these things after they're placed? I don't know if I've tried that. Can I? Oh, look at that. I can, and it breaks everything. That sucks. I was hoping it would keep them there. Great. Well, that one was easy. I like the easy ones. They provide a little, like, appetizer. We're getting close here. Okay, so now we're almost able to unlock this. What are our choices? Adding bytes. Add the 2 input bytes. Each output bit in the output should be a result of the addition of the corresponding bits from the inputs and potentially a carry. If the result does not fit in 8 bits, turn the output carry. You can think of it as the 9th bit. Finally, there's an input carry as well. This is useful for chaining together byte adders to add larger numbers. So in nand2tetris, you would typically start by implementing a half adder, which does not fully handle carry inputs, and then use that to implement a full adder. Let's see what the hint is. You only need 8 full adders. Okay, well, great. I see. We must have already done the half and full adder in the last episode, and I just don't remember it. Oops. Misc. Add. There we go. Full adder adds 3 inputs and returns a sum and a carry. And so then these are, again, byte inputs, I guess? Input carry. I wish they called this carry instead of in. Well, they gave us this hint that we only need 8 full adders, so let's go ahead. Let's do this for 1. All right, we know we're going to want to split each of these. Oh, I hate that these are not close or are too close. Can I move them? I can move them. Thank God. Okay, what I do is I want these close but not on top of each other. All right. So I believe we want to add the corresponding bits, right? So we'll put the carry to input 1, that to input 1, and that to input 1. And then what are we doing with it? We've got an output here, and the output, that's our result, and that's our carry. So I think what we're going to do here is the classic cascaded series of adders. So the carry is going to go here, and whether or not it's correct, whether or not it's on, rather, it should do the right thing. Famous last words. Third one here. Carry's going to go here. This is, again, going to get messier than I'd like. If you were designing a CPU for efficiency, you would not do what I'm doing here. And the reason you wouldn't do it is that you're basically setting up a long series. You're setting up these things in series. And I talked the last time, or I've talked in other videos, I don't remember if I talked in the last Turing Complete video, that we kind of ignore time when we're dealing with combinatoric circuits. We pretend that time doesn't exist, but we're only pretending that, right? Propagation delay does exist in the real world. And if you set up a chain of, 32 of these things, you really are going to have to worry about propagation delays. All right, so now we've got a byte maker. And I'm just going to put that right there because I like having it very close to where it's going. And then we wire these up in series. Not in series, in parallel. Each to its corresponding bit. I guess I can zoom out. That gives us a little more room to play with. All right, I feel like that's probably a reasonable multi-bit or byte adder. Let's take a look. Runs a bunch of tests. Fabulous. And now we have our byte adder unlocked. That brings us over here. And what do we got? A switch. So that's a mux. That's kind of exciting. Over here we have byte not, an inverter of a byte, I guess. And over here we have byte or. Those seem pretty straightforward. And that brings us to negative numbers. Well, let's do the switch first because I like that idea. Create a component that switches an input byte on or off. Switches an input byte on or off. Again, I have trouble with some of their descriptions. I'm not quite sure what they're saying. Output the byte if the switch is on. Well, we're probably going to need to split this byte into its constituent bits, and we're probably going to need to reintegrate it at the other end. In fact, let's give ourselves a little more space because I think we're going to need it, frankly. Let's do this circuit for just one bit. See if we can get that right. So that on, we want that on. And really, this bit is going to go here only in the case when that is on, right? Oh, did I do the wrong bit here? I did. There we go. Right. And then in every other case, if that's off, that should be off. And if some other input is on, it shouldn't affect it. And if that's off, it should be off. So that looks right. And I think we can literally replicate it for each one of these bits. Now, this is something where, again, in nand2tetris, you would have earlier on created a, essentially an 8-bit AND that speaks this bitwise. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And I think I'm wrong that I will not need that. So let's just go ahead, wire these up. I know that I'm complaining about some of the things in here and the UI, and I'm picking nits, but it is a remarkably polished game. The animation feels smooth. I do understand what it's trying to get me to do without a lot of effort. So, take my whining for just an old man being persnickety. I'm very impressed with this game. And I look forward to seeing it develop over time. I do not regret the purchase of this one bit. And very often with early access games, big promises are made and then never delivered. I would say even though this is early access, it's already delivering its promise. All right, we're going to run our tests, and it looks like we've done that. And we now have unlocked a switch. So that brings us to the input selector. See, I would have thought the input selector would have been, even though he did not pass our test, we decided to keep the dog. Unlike most earthlings, he's fluffy and follows simple instructions well. Oh, I think they're giving me a little hint here. We might want you to team you two up since you complement each other's shortcomings well. I wonder if they're telling me that this is going to be a twos complement. When the bit selector input is red, output byte A, otherwise output byte B. So this is a bit input. This is an output. All right, so I see why they wanted to do it this way. So what we're going to do is we're going to use, this seems very wasteful to me. Obviously, we could do this with gates similarly to what we just did, but I think what they want us to do is use the switch component. Let's give these things some values so we can see them. Oh, that's very nice. I like that quite a lot. That's sweet. Okay. And then we can bring this one. Well, did I remember it right? When it's red, output A, otherwise B. This must be A, I think. It's not labeled right now. Hey, there it is. I actually had this wrong. When it's red, output A, otherwise output B. Right. Okay, so it's red, and this is A, and A is coming through. And then when we switch it on, B comes through. Now, do I have an 8-bit NOR, an 8-bit OR? I do not. God, that's the worst. Oh, it's fine. This is not what I think of as a reasonable solution to this, but it's going to work. So just going to do that. This feels awful, but I think it's going to work for purposes of the game. Since we're guaranteed, so we've basically implemented this switch here where we're guaranteeing that one of these wires is going to be 0, we can just add them together and treat this as essentially a bitwise OR. Saving bytes, you know, that sounds complicated and it's getting up towards memory. So let's start working our way up this other side of the tree next. All right, we'll start in the very left. Oh, here's our byte OR that I was talking about. Pairwise OR together each bit. Ooh, burn to any non-vegetarian out there. Or each bit of the input and output the result. So do we have the splitters here? We do. Put them right here. And then we're going to do the makers, which are going to be over here. We only need one. Eep. Get rid of that to get a little more space. That feels much nicer. All right. And then we're going to use 8 OR gates, I think. 1, 2, 3, 4, 5, 6, 7, 8. And yes, I did leave a little gap there on purpose. So we're going to OR together each bit, bitwise. You know, I was there complaining that I didn't have this on my other levels, and now I'm wondering if as soon as I finish this, they're going to unlock those, and I could have used those if I'd just done these in order left to right. Well, it'll be interesting to see. Match up our 64s, and then our 128s, right? And then each of these just goes there. Hope it's interesting to watch this. I don't always know. No, what did I get? What did I do wrong? Yeah, it helps if you actually hook up things on the front end. I get a lot of feedback on my game videos. I get a lot of feedback on my technology videos. And the technology gaming videos, I get like 1 or 2 weirdos, and you know who you are, out there will say, wow, thanks for showing this. I kind of suspect I'm losing most people with them. I don't really care. I'm going to keep doing them because I enjoy them. All right, so here's our byte OR that has been unlocked. Well, now I want to go back. Let's say we'll go back over here. No, I don't see the byte or. Okay, so that's a relief, I guess. It means that it wasn't completely a complete joke, that I implemented that by hand, or like this essentially byte and that I did. All right. So then we got this one, byte not. Previous model of brain size being the main predictor of intelligence was naive. Tool making and usage. The number of arms on a creature is the main predictor of intelligence. Not each bit of the byte input. Well, this one feels like it's an even easier version of what we just did. This time, let's remember to hook up all of the bits and bobs. 1, 2, 3, 4, 5, 6, 7, 8. So one thing that various games of this type do, and digital does it, and Logisim I think also does it, is this behavior where if you put a component on another component, it will essentially connect the wires. The Silicon Zeros by Pleasing Fungus Games did this as well, and it's a very satisfying UI, and I'm missing it here. I wish I should write to the developer and suggest that as an enhancement. Yay, and we have a byte not. Okay, what's this one? Negative numbers. All right, I think let's do negative numbers today, and then that might be a good place to stop. I like the idea of doing this as a short series of bursts, and then we can get up to the arithmetic and memory line in the next video. They're going to explain a little bit about 2's complement, probably. I don't understand what they're showing me here. I think they're saying that I should be testing here. I can change this. Oh, I see. They're basically going to lead me to 2's complement, I think. So the requirements are, we should be able to represent negative 127 to 127. And I think they're telling me here that I can't, that I don't meet that requirement. Well, this is a clever way to lead us to it. Since we never need to represent 128, we clearly don't need this to be 128. So we'll make this be negative 1, let's say. And what happens? No, that's just minus 1. How about if it's minus 128? Let's put all of these on. And then if this is on, that's negative 1. That was it. UI there was very confusing. I think anyone who does not already know 2's complement notation is never going to clear this level. So that's some feedback that I have for the developers. All right, I think this is a good place to stop. I've enjoyed walking you through these next few levels in Turing Complete, and I will see you next time. This has been Gaming Like It's 1979. Thanks for watching.